Now, by inspection also you can find out these values, because if you subtract, when I subtract lambda from the principal diagonal, I get, that is 3. Though the diagonals have been scaled, but the directions are held on to, that is the span of these diagonals do not change, and that is where the eigenvectors are those which hold on to their span or direction even under transformation. Now let's try and find the eigenvalues and eigenvectors of the transformation matrix and then interpret them physically. Now, one of the methods that you could follow is the basic conventional method. Subtract lambda from all the elements of the principal diagonal and find the determinant and equate it to 0. You get the characteristic equation and hence the roots, which are nothing but the eigenvalues. In this case, when I do that, I will get 2 minus lambda whole square minus 1 is equal to 0. And if I take square root on both sides, I get 2 minus lambda is equal to plus or minus 1. And when I simplify, I get lambda either to be 3 or 1. That means the two distinct eigenvalues possible for the transformation matrix are 3 and 1. Now, by inspection also you can find out these values, because if you subtract 1 from both the principal diagonal elements, you get 1, 1, 1, 1, which means the determinant goes to 0. Or since the product of off diagonal terms is 1, you should reduce the principal diagonal element product also to 1. So either you can have plus 1 or minus 1 minus 1, and if you put minus 1 minus 1, the eigenvalue turns out to be 3. So by inspection also you can reckon these two values. Now, when I subtract lambda from the principal diagonal, I get, that is 3, I get minus 1 minus 1 plus 1 plus 1. This means my eigenvector obviously has to be 1, 1. That is, if I multiply this minus 1 and then plus 1, I will get 0. Of course, this can be 4, 4, 3, 3. Of course, it is a unit vector, it has to be normalized. But if you are just seeking the span of the eigenvector, it is just 1, 1. And since it's a unit vector, it can be normalized. It can be 1 by root 2, 1 by root 2. Of course, now here we are seeking only the span of the eigenvector, so it is 1, 1. And in terms of slope also we will interpret, and in terms of diagonal scaling also we will interpret this. Now, coming to the second eigenvector, that is when you subtract 1 from both the principal diagonal, you will get plus 1 here, and therefore the eigenvector happens to be 1 and minus 1, the span of the eigenvector. So that means if I substitute 1 and minus 1, since both elements are plus, here also both elements are plus, what we will get is 0, 0. So therefore, one eigenvector is 1, 1, another eigenvector is 1 minus 1. So therefore, we have 2 eigenvectors and 2 eigenvalues. Now let's try and interpret them with respect to the geometry of transformation. Now let's try and interpret the eigenvalues and eigenvectors geometrically. Please observe figure number 1. That is, I am talking about both magnitude and direction of the diagonals of the square space to begin with. It is easy to compute that the diagonals of the square are root 2 and root 2, and both these diagonals happen to be perpendicular to each other. That is, the direction of each diagonal is at 90 degree to each other. You can see that one diagonal makes an angle 45 degree, the slope is plus 1. Another diagonal makes an angle 135 degree with respect to positive x-axis, the slope is minus 1. And since the product of the slopes is minus 1, these two diagonals are perpendicular to each other. Having understood this, now let's look at the transformed square, that is the rhombus I am talking about. Here the larger diagonal has the value 3 root 2 and the shorter diagonal has the value root 2. You can see here, and you can see if you looked at the coordinates of the endpoints of the larger diagonal, it is 0, 0, 3, 3. So the slope obviously happens to be +1. It makes an angle 45 degree to the positive x-axis. And if you looked at the shorter diagonal, the coordinates are 1, 2 and 2, 1, and you can easily reckon the slope to be -1, makes an angle 135 degree with respect to positive x-axis. So the reckoning from these observations is very, very simple, though the diagonals have been scaled. Okay, though the diagonals have been scaled, but the directions are held on to, that is the span of these diagonals do not change, and that is where the concept of eigenvector comes into picture. And you can also see that the diagonal 1 is scaled by lambda 1. If I say the first eigenvalue is 3, then it gets scaled by the eigenvalue and it becomes 3 root 2, and the second eigenvalue is 1, so therefore the diagonal gets scaled by 1, root 2 into 1 is root 2. But what is also to be noted that the eigenvectors are those which hold on to their span or direction even under transformation. Now, if you recall the eigenvectors that we calculated using the standard conventional method, the eigenvector that is associated with eigenvalue 3, that is I am talking about lambda 1, which in fact scales the diagonal and makes it the bigger diagonal, and the eigenvalue corresponding to that is 1, 1, and this clearly says that the span of the eigenvector is along the diagonal 1, which you can see in the figure, and as far as the eigenvector 2 is concerned, and that is given by -1, +1, or you can also choose +1, -1, it does not matter, and you can see that is actually perpendicular to the first diagonal. The span of that eigenvector is perpendicular to the first diagonal. That means the slope of the second diagonal is -1, and that diagonal is scaled by the second eigenvalue, that is 1, and the corresponding eigenvector is given by either this, or you can also choose that to be +1, -1. Now you can clearly see that the eigenvectors that we computed in the previous discussion in fact coincide with the direction of diagonals, and these diagonals are scaled by the respective eigenvalues. So the diagonals were perpendicular even after transformation. They continue to be perpendicular to each other, and that is where we very, very categorically tell you that eigenvectors hold on to their span despite the transformation, and these eigenvectors are scaled by the eigenvalues. That is where you see that each diagonal is scaled by the eigenvalues, and this once again goes to explain us why exactly we say the eigenvectors continue to hold on to their span or direction. Sometimes eigenvectors may get reversed because they get scaled by a negative eigenvalue, but in this case, since both eigenvalues happen to be positive, they not only go to hold on to their span but also continue to maintain their directions. So despite the transformation, in fact, if you look at the original square, there also if you look at the directions of both the diagonals, they are 90 degree to each other, and the slopes being +1 and -1 respectively. So this is where we interpret the eigenvalues and eigenvectors in the practical sense. And also please remember one thing: the product of these eigenvalues, that is 3 and 1, is nothing but area of the rhombus, because that is also equal to the determinant of the transformation matrix. This fact we had established during the discussions of beginners module, the product of eigenvalues is nothing but the determinant of the matrix, and here the transformation matrix that we used is given by 2, 2, 1, 1, and whose determinant is of course 3, and since we got two eigenvalues 3 and 1, their product is nothing but the determinant, which is nothing but the ratio of area of the rhombus to that of the square, and therefore we get 3:1. So we have not only interpreted the fact that the ratio of the areas after transformation is nothing but the determinant of the transformation matrix, we also emphasized on one fact that eigenvectors which get scaled by eigenvalues continue to hold on to their span. In this case, since both the eigenvalues happen to be positive, the eigenvectors continue to hold on to their direction also even after transformation. Now, one more observation that you may want to make here is that both the eigenvectors that we have got, since they are perpendicular to each other, their inner product in fact goes to 0. They are orthogonal to each other, and of course if they are orthogonal to each other, naturally they have to be linearly independent, and that fact is also established. And since they are linearly independent, if you construct a matrix with these two as columns, then their determinant is also non-zero.